So in this lecture, we're going to discuss the third step for traffic demand forecasting under the four-step forecasting model, and that is the modal split.
So next step for our forecasting model is our modal split. So the modal split is also known as the mode or the mode split or modal share or mode share. So in this step, the percentage now of the travelers using a specific type or mode of transportation is determined, or the number of trips using a specific type of transportation is computed. So the choice may be done using either the binary or a multiple choice. An example of binary choice would be, if we have here a trip, so we could choose as a type of transportation is a non-motorized transportation or a motorized transportation. And in non-motorized, our travelers could choose either to walk or to use a bicycle. And for motorized, they could use or choose a private or a public type of transportation. So the private type could be a company car or a personal car. And for the public, this could be a rail transport or a bus transport. So binary, ibig sabihin, there are always two choices for each mode. So for modal split, we are going to use basically the generalized cost, the same that we use for our trip distribution. So this places the cost on a quantifiable and sometimes unquantifiable factors that may be incurred, or this are the factors included in your generalized cost. So they may be incurred during a trip using a specified mode. So this would include our travel costs, your travel time, and our travel distance. So this may also include the level of service that is experienced by the trip goer. So for our generalized cost that is used for our modal split, this is now computed as C plus DT, wherein C is our cost, D is the time value, and T is the time incurred. So for modal split, we have different methods or models used. We have the first one, which is what we call the disaggregate choice model. So this assumes that the trip maker would select mode which provides the most economic utility. The total utility provided by mode option will now be computed as U sub m is equal to beta sub m plus the summation of alpha j times zmj plus epsilon. So the models, depending on the distribution of E now, will be either as the Probit model or a normal distribution of your E, and the logit model, which follows the Weibull distribution from your statistics. So for the equation given, we have now U sub m will be our total utility provided by the mode of transportation or the option choice, which is m. And then we have bm, which is the mode specific parameter, which is the relative attractiveness of different travel modes within segment. aj will be our model parameter. zmj will be the set of travel characteristic of mode m in terms of travel cost or travel time. And e is our stochastic term, which would make allowance for an specifiable portion of utility assumed to be random. So the variability in individual utilities around average utility in a segment. So for our Probit model, this now assumes a normal distributed error in choices of transportation mode. So basically, the equation for a Probit model will be given by this equation. So for the logit model, this is the probability, or this computes for the probability that a trip maker will select one mode option M, which is equal to the probability that the option's utility is greater than the utility of the other options. So the general equation now for the logit model is given by P sub M is equal to E raised to U sub M divided by the sum of E raised to U sub M prime, wherein P sub M is the probability of the mode M chosen. M prime will be the index over all modes included in chosen set. So remember that for logit model, when only two choices for modes is given, the equation now can be simplified into a binary logit model, which is equal now to this equation. So P1 now will be equal to 1 divided by 1 plus E raised to U sub 2 minus U sub 1. So to understand modal split, let us solve an example. So for a particular zone pair, three modes of travel between the zones exist. So we have the private transport, the bus, and an urban rapid transit system. So given that all the trip makers have access to private transport and that the perceived utility of a mode is given by the equation U sub m is equal to negative 0.004 T sub m minus 0.005 C sub m minus 0.003 U prime sub m plus 0.15 D sub m, wherein T sub m is our travel time in minutes, C sub m is the travel cost in pesos, U sub m is the waiting time in minutes, and D sub m is a dummy variable. So let's assume that the variable values are as shown and that there are 1,000 trips to be made from the origin to the destination zone. Let's determine the number of trips made by each mode using logit model. So we have here the table for the values. So for our solution, we first solve for the utility for each of our transportation mode. So from our given equation and the given values for each mode, so we just substitute our values from this table to this equation. So we'll have now for U private, so that is 0.004 times 65 minus 0.005 times 60 minus 0.003 times 0 plus 0.15 times 1, giving us a value of 0.41, which is negative. And then for the bus, now substituting the value for the bus will give us negative 0.445, and for the transit system gives us a U sub m of negative 0.265. So we now use our logit model to compute for the probabilities for each transportation mode. So we have the equation e raised to U sub m divided by the summation of e raised to U sub m prime. So we have here our mode of transportation, the private, bus, and your transit. So we have our computed U sub m, and then for our e raised to U sub m, it will give us now a value of 0.664, 0.6421, and 0.767, which is a total of 2.072. So computing now for our probability, that is now 0.664 divided by the total 2.072, giving us 0.32. For the bus, will give us probability of 0.309, and for our transit, it will give us a probability of 0.370, which is, when we sum up, will be equivalent to 0.99 or almost equal to 1. So with this, it would simply mean that for a 1,000 trip made in our study area, there will be 320 times the 1,000 trips. So there are 320 trips that are made using private cars. And then we have 309 trips that are made by bus. And we have 370 trips that are made by, or that is made using the transit system, which is approximately equal to 1,000. So next example for the modal split. So let's use a logit model to determine the probabilities of a group of 5,000 work commuters choosing between three modes of travel during the morning peak hour. So the three modes now are the private car, the bus, and the light rail. So the utility functions are estimated now using the following. So for the car is now given by the equation 7 minus 0.2c minus 0.03t. The utility for the bus is 2 minus 0.2c minus 0.3t. And for the utility of the light rail is 4 minus 0.2c minus 0.03, wherein c now is equal to the cost in Philippine peso and t is equal to the travel time in minutes. So for all workers, the driving cost will be 60 pesos with 20 minutes travel time. The bus fare now will be equal to 20 pesos with a 40-minute travel time, and for the rail fare, it will be 38 pesos with a 25-minute travel time. So for our solution, we just compute for the utility functions for each mode using the respective equations in the given transportation costs and transportation travel time. So for driving costs or the utility function for private cars, we have 7 minus 0.2 times the cost of 60 minus 0.03 times the 20-minute travel time, giving us a value of negative 5.6. Then we have for the utility of the bus is 2 minus 0.2 times 20 minus 0.03 times 40 will give us negative 3.2. And for the utility function of the light rail system, we have 4 minus 0.2 times 38 minus 0.03 times 25, giving us a value of negative 4.35. So to compute for our probabilities, we can simplify our solution by using our table. So we have here the mode, our transportation mode. So we have the car, the bus, and the light rail system. So we have here the next column is our utility functions, computed values, or negative 5.6, negative 3.2, and negative 4.35. And for upper e raised to u sub m, so e raised to negative 5.6 will give us 0.0037. Next, we have e raised to negative 3.2, giving us a value of 0.0408. And e raised to negative 4.35 will give us a value of 0.0129. So our total now is 0.0574. So next we have our P sub m. So we know that P sub m now is simply equal to e raised to u sub m divided by the total. So for this value, we have 0.0037 divided by 0.574. So we have 0.0645. Then we have 0.7108 for the bus. And then for the light rail system, we have 0.2247. So it will give us a sum of 1. So we can compute for the percentage of our trip makers using the different modes. So we have 6.45% of the workers using car or the private car. Then we have 71.08% of the workers using the bus and 22.47% traveling using the light rail system. So for the number of workers now that uses each of our mode of transportation, we simply compute this number of workers by multiplying our probability to the total number of workers. So in our problem, we have 500 workers that are choosing that will have to choose between these three modes of transportation. So from here, we can see that there will be 323 workers that are using private cars. So we have 3,554 workers that are using the bus and 1,123 workers using the light rail system, or a total of 5,000 workers. So that's how you use your modal split.
So that's it for the third step or the third submodel for the four-step forecasting model. Next lecture, we're going to discuss the last and the fourth step for traffic demand forecasting. Thank you for listening.